Eric,
Omar,
I'm in my basement, in the bunker of bunkers, because you have managed to embroil us into another series of controversies that, unfortunately, I would love to introduce our guest today, Mr. Sooper Gforce, but I can't even do that. I can't do my obligation because we have to get these apologies out of the way.
you knew you were getting this when you decided to start a podcast with the most controversial figure in evidence-based fitness. So,
And that's saying something.
I'd say it is saying something. So I would apologize, but I feel like you brought this upon yourself.
I should have known better.
You really should have. I take no responsibility for my responsibilities. So, in complete contrast to that, I want to take some responsibility and take a moment to give two shout-outs. One, to Mr. N1 himself, Kasim Hansen. Those who've been listening, it was a little while ago we did kind of a series discussing the meta-conversation of the role of science and the role of evidence-based fitness and some of the frustrations and the challenge of actually putting out content that is watched, read, received, and actually utilized while also being useful and science-based in the modern game, especially with the focus on YouTube. We had Dr. Pack. We had Milo Wolf. We had the young up-and-comer himself, Mr. Grilled Cheese Sandwich, coming straight out of the Schoenfeld lab. We had a really good roundtable with a lot of these up-and-comers, Max Coleman. It was awesome. And one of the things that I said, which I want to be clear on, I got a little bit wrong, ironically. I alluded to a reaction video that was done that Kasim did, and I thought it wasn't very charitable. And the thing that I didn't note is that it was actually a reaction to a reaction. So our critique of the reaction video, reacting to a reacting video, a little bit of irony there. The take-home message, I will say, first off, I do love Kasim's content. And I think sometimes, and in many ways, he's been a victim of the, hey, you're just overcomplicating it, just train hard, bro. But I think it would be great if each time we interacted with other people's content or reacted to it, we really leveraged the principle of charity. And I think that's something we've talked about before. But just the idea of asking yourself, looking at the man in the mirror, am I being as charitable as possible in my interpretation of this person's content, given all the complexities of trying to play the game as we need to get information out there while also sharing useful information and not subverting scientific thinking in and of itself. So I'll just say, hey, Eric Helms got that one wrong. I'm going to try to show people that, hey, I will hold myself accountable. And do definitely follow N1. Good stuff. Another one that I want to give a shout out to is Dr. D'Souza. So one of the authors on the much maligned Ennis paper on 52 sets, the high volume work, he reached out to me, had some very nice things to say about the podcast. He's an avid listener, which was awesome. Shout out to you. And one thing that he mentioned was that, hey, when you're talking about science communicators and how they're perceived in the scientific community, the so-called Sagan effect, just got to be careful with how that comes across. Because one thing that I did say was that on average, when you look at people who have more science communication efforts, they also have slightly more publications on average. And that is an average. That's not a statement about everyone. This is data from a 2016 paper. And I'm certainly not suggesting that all people who are traditional kind of pathway researchers or professors are lazy or less productive. And I'm not trying to call anyone out. I just wanted people to understand that just because someone's a science communicator does not mean that they're also not potentially a highly productive academic, if they're even still in academia. And just encouraging us to think inclusively and giving shout outs to those who deserve it. A lot of people are doing really good work who are just simply don't have the time, the energy, or the clout, or the ability to invest the time and money, like we talked about, into being a science communicator that's effectively reaching a large audience, which is why we at Iron Culture really try to bring on a lot of young and up-and-coming academics to help them get a platform to communicate more science and more information that is practically applicable to you, dear listener. And to that effect, we have newly minted Dr. Wes Goodman on. I had the pleasure and privilege of being his external committee member while he was doing his PhD with a focus in biomechanics out at Montana State University, led by David Graham, his principal advisor. And he is not only someone who is a biomechanist doing really cool stuff in the lab, doing musculoskeletal modeling and unique analyses, which I'll plant a little seed on induced acceleration analysis, and you'll learn what that is and why it's important and what gaps it fits in the biomechanics literature and our understanding of things. But also, the man's an actively competing Highland Games competitor, also strongman dabbler, and like me, was considered good in powerlifting before powerlifting itself got good. And he's got a master's. He's got CSCS. He lectures, or at least it was an adjunct lecturer for both advanced strength conditioning as well as motor control. And he's working in clinical settings. He owns a gym, like Iron Strong Performance. Am I saying that right? Probably not. In Bozeman,
like Iron Strength and Performance.
Like Iron Strength and Performance out in Bozeman, Montana, where he's got a hardcore group of dedicated lifters doing the damn thing. So yeah, Wes, welcome to the podcast.
Thanks for having me. Glad to be here.
I love it. So I think it would be really useful to talk through essentially what is the field of biomechanics? Do we need it? And what have we learned from it? Generally, the way you see it, to start, kind of just big picture. What's biomechanics, man?
All right. Well, biomechanics in my mind is the mechanics of living systems. Now, I specialize in human biomechanics, especially resistance training biomechanics. Other people study mechanics of, other animals, stuff like that. But typically, we're applying Newtonian mechanics to investigate things like, joint reaction forces. From my perspective, took that a little bit further, trying to calculate or estimate muscle forces and the consequence of those muscle forces on performance, injury risk reduction, and stuff like that. So that's a very broad overview. I think biomechanics oftentimes gets a bad rap and oftentimes is misunderstood. I think a lot of times when people hear biomechanics in the lay public, they think of things related to technique, maybe things related to just anthropometry, basic things like kinematics, what are the, joint angles and velocities, with certain movements and stuff like that. And that's kind of where they leave it, but it gets more complicated than that. I think the role of biomechanics in injury is somewhat controversial. We can talk about why that might be the case in a little bit, and then I can give you some of my opinions on those things. But I think that's kind of like the 10,000 overview of how I view biomechanics.
Omar, I feel like biomechanics is one of those places that generates a fair bit of things that are perceived as bro science, or is often leveraged in relatively biased ways. And someone can take the same data set and say very different things. And like, for example, there's a lot of people who will state things like your knee shouldn't go over your toes, or you shouldn't squat to depth, or this type of squat is injurious to the back or your knee. To me, it seems like a place where there's a lot of, I wouldn't even necessarily call it pseudoscience, but at least misunderstood and misapplied science in the evidence-based space more broadly. I don't know if you'd agree with that.
Yeah, I think it's actually interesting enough, even worse outside of the evidence-based space, where I think, referencing TikTok, which, the forgotten episode, Eric, where I said you should get on there, where a lot of, let's call them, I suppose, the movement optimist bros, like in terms of you need to do it this way because of A, B, C, D, and they'll give a, in quotations, biomechanics rationale. It's absolutely probably at the pinnacle of it being misapplied, but it's essentially just a catch-all of something that sounds right to a lay audience, maybe what Wes was alluding to, where they could then leverage that for their arguments. I think like probably right now in the last handful of years, because everyone wants to perform. First, it was for strength, how to perform the squat most efficiently to lift the most weight. I'd say in the last 2 to 3 years, there's been an increased focus on hypertrophy, and in particular, how to perform particular movements in order to, in quotations, maximize hypertrophy. So that personally to me, Eric, is where I see it probably the most misapplied to the general audience.
No, I would agree. And you can see this in a lot of areas too, and there's almost like levels. Like there are people who are researchers / practitioners making claims in discussions that maybe are a little inaccurate and then making posts about them. There are personal training education materials that are accurately representing some data, but then overreaching on it. A good example would be some of the models that are in, and don't get me wrong, I like this organization, NASM. You and I, Omar, were both certified by them. They both do a lot of good work, and they are absolutely evolving. But some of the theories from, say, physical therapy from 15 years ago that kind of made their way into some of the NASM foundational information, like, oh, this muscle is weak, this muscle is lengthened, or it's shortened, so you need to foam roll this, strengthen that, and that's going to fix your muscle imbalance. There's even question marks around the concept of muscle imbalances, right? Let alone the efficacy of those treatments to quote unquote fix those issues. So it's pretty well embedded. And I think it'd be really useful, Wes, if we can talk through where do these truisms, pseudoscientific-esque ideas, and what theories are there that are out there that some of our kind of general fitness space biomechanics knowledge is based upon, and are they well behind the current biomechanics understanding and theories of the way things operate? So I actually, right before this podcast, we were literally in the biomechanics lab here at AUT, and we're working on calibrating our new 3D system for a pretty cool study. We're going to be evaluating how well judges in powerlifting can assess depth based upon where they're sitting using a 3D marker system and actually marking up the person, doing a anthropometric profile, as well as assessing where objective depth is with 3D cameras and then looking at 2D cameras. And we're going to do a whole research project on this. In our biomechanics lab, we have synchronized force plates, 3D cameras, 2D cameras, marker-based system. We can also integrate EMG with it and do a few other cool things. And if you look at most of the research, we're looking at 2D analysis, 3D analysis, force plates, what's called a linear position transducer, which is just tracking displacement to then derive, velocity and angles, and also EMG. And from those various things, we can estimate certain qualities of a movement and potentially the muscular involvement and the joint forces, torques. And this falls under the broad umbrella of kinetics and kinematics. So kinetics is the forces involved, and kinematics also includes some of the joint movements that are involved, and a description of where you actually are moving in space. And when you read some of the research that has come out of this, especially you'll see some of the stuff that we were talking about is citing stuff from the 80s and 90s and making assumptions about long-term adaptation from these acute measures, or like we talked about before we started recording, would you call it necromechanics, Wes?
Yeah.
So talk to us about some of these methods, their limitations, and what necromechanics is and why 40K is awesome.
Sounds good. Yeah, there's lots to unpack there. So I think to start going back to what you initially started about with, the NASM and some of, this goes beyond that too. You still see this in ACSM guidelines and some of their chapters. They talk about, weak muscles, short muscles, long muscles, stuff like that. Oftentimes they're not followed by a reference, or if it is followed by a reference, if you look into the reference, that's not what the reference actually, you can't really conclude that from that anyway. And so in my mind, I think a lot of this comes from engineers working in biomechanics, and they're trying to get a good understanding of the forces involved and when some type of material will break and stuff like that. And they're usually dealing with inert substances that don't adapt. And I think a lot of the times when we measure these things, we see, force values that oftentimes look kind of large, or, they're large enough in a cadaver model to break something. Again, some of the issues with that would be the cadaver's no longer living. It's not adapting to these stresses. And so I think things get really messy. I also think that in the biomechanics community, and actually not just the biomechanics community, but any type of scientific field where it's really hard to get people to comply to, long-term training programs, or it's unethical to set up a design of a study where we're going to try to injure someone. We try to find these, variables that we can associate or predict injuries. and things end up getting, really messy. I think another thing is, going to some of the, American Society of Biomechanics or International Society of Biomechanics conferences, not even all biomechanists agree on these things, right? There'll be hot debates about the role of like knee valgus, right, and ACL injury risk, with some people really saying it's not a great predictor, and others saying, well, no, it is in certain situations, right? So I wouldn't even necessarily just blame lay people when you still have scientists arguing about this stuff. So just things get kind of messy. I'd be happy to toss some of my opinions. I will state that there's some stuff that I think has a decent amount of evidence to support, but then some things, like I was mentioning, are really, really hard to study. And it's kind of where we have to come in, speculate, maybe use a little bit of reasoning, but it could be wrong.
No, I wouldn't blame the layperson either. In fact, I think there's actually a fair amount of, there's structural blame, where I think there is issues related to how do we update the record, what new studies can be done, how is it interpreted, and like, for example, we ran into this. If you publish in, say, the Journal of Strength Conditioning Research, and it is all acute-based data on a model, and they have a section called practical applications where you have to say, this, it kind of forces you to speculate probably more than you otherwise would have if you published in the Journal of Sports Biomechanics or whatever. And then, practitioners see that, and not being researchers, they'll take it a certain, way, which is very understandable. And if research is no longer being done on a certain area, and you're left with studies from the 80s or 90s on EMG, and the understanding, like Andrew wasn't alive in 1990 or 1980 to talk about Vygotsky, by the way, to talk about the limitations of EMG. Like, our understanding of what these methods can and can't tell us, we're sometimes creating narratives based upon an old understanding of the science. And I don't think that's really anyone's fault. It's more of a structural issue. But I would say, like, if we try to trace back all the way, where does the fear of squats causing knee injuries come from? It's from short-term biomechanics studies done, decades ago. So maybe what would be helpful right now, Wes, is if you could help us understand what methods are being used. Like you briefly talked about inert tissue, like we are actually doing cadaver studies because it's hard to measure injuries in people. We can't go, right, we're going to squat until you blow your patella off your knee. What are some of the foundational learnings we have in biomechanics, and how did we develop them, and what are their limitations?
Yeah, I mean, there's a lot of approaches to this. So some of the things that we can directly measure in the lab would be, like you were mentioning, Eric, in your lab, you have a motion capture system and force plates. And so a lot of times people make simple biomechanical models to try to estimate the joint reaction forces and moments or turning forces at a given joint, while changing external conditions. What happens when we squat deeper? What happens when we put weight on the bar? And typically those values will go up. And then people will say, oh, if we squat deeper, the knee moment goes up. Therefore, maybe if someone is at risk for developing a knee injury, or they're rehabbing from a knee injury, maybe we shouldn't do that. But that's kind of where it stops. Like kind of like we were talking about with a lot of the applied strength and conditioning journals, you're asked to speculate about practical applications, right? And so no one ever actually did that in a rehab setting. They just said that because this force value is higher, we therefore think it would be smart to avoid doing this. And a lot of times in medicine, we're pretty conservative. We don't want to hurt people. We don't want to be sued. We don't want to do a lot of things. Right? So there's a reason for it, but it's not backed by hard empirical evidence that showed a group that squatted 85% of their max compared to 50% of their max showing more injuries. And so another way to study things would be retrospective studies. So, you look at a bunch of people training, maybe you see people who are, squatting, really deep, or people who are using high loads, and we can compare the injuries, between people who are squatting above parallel compared to below parallel, or, squatting with lower percentage of their 1RM or a higher percentage, and then kind of just follow them throughout and see what happens. So those are the things that we can do, but rarely are we running prospective studies where we try to have an intervention to see which group gets injured, because no IRB will prove that, right? So we're kind of stuck. Sometimes I get frustrated when people say, where where's the reference, where's the citation? I get what they're saying, but sometimes it's like, well, we might not ever have that, So we kind of have to work with what we have. We need to be, reasonable, but we also have to understand that some of the other claims that you see in like NASM and ACSM aren't well founded. It's kind of just a best, conservative guess.
Yeah. And I mean, if we go all the way back, we're talking pre-modern era, pre any of this technology, our first understanding of anatomy did come from studying cadavers and cutting open dead bodies, and then even electrical stimulation of, certain tissues. So we have an anatomical understanding that tends to be pretty reductionist. And you can see the roots in that in even modern thinking. Some of the pushback you got on a lot of your research was that when we started talking about forces being generated to impact, say, the barbell on someone's back, and it having an impact on a specific, joint coupling, but the muscle didn't cross that joint, we had some reviewers who really struggled with that. Kind of the idea that certain muscles can exert forces beyond the traditional kind of reductionist view. So can you talk a little bit about the limitations of some of these methods and where does your research step in to kind of fill that gap and help us make some maybe more accurate understandings? And I understand if you need to talk more about biomechanical theories for us to even kind of get that to start, then the floor is yours, sir.
Yeah, we'll start there. So in biomechanics, a lot of us who have gone through some type of, biomechanics class are probably used to seeing free body diagrams, right? Where you have a simple like stick figure and vectors pointing in different directions, saying like muscles and how they're pulling in their forces and stuff like that. And so classically, we had these pretty simplistic diagrams and we had solved for, something right around a given joint. And then we do like a recursive operation and solve our way up the chain, right? Solve for what's happening at the foot, to the ankle, the knee, to the hip. What ended up happening, and I think technology plays a role in this as well. As computers became more powerful and we could run more complex simulations, we could start making these models a little bit more complex. And so I didn't obviously come up with this. I'm just a user of these tools. A handful of people have been doing this for a long time. And so basically what people would do was they would make a more complicated musculoskeletal model, and they'd start including muscles, of the entire lower extremity or whatever. Like, let's say you're interested in jumping or running or something along those lines. And then they would basically calculate or estimate the amount of force that each muscle could produce. We can get into how you actually go about doing that in a little bit. And then the consequence of that force on performance of the task or accelerating the limbs in different directions. However, because everything is connected, muscles can actually accelerate segments they do and they don't cross. And they can also transmit forces between segments. And so, for example, the soleus, when your calf muscles, can actually have a contact force at the hip, even though it doesn't cross it, through this concept of dynamical coupling, where the inertial properties of one segment are highly dependent on what's happening at another segment. These things are really hard to model, and that's why we also need these mathematical models in silico to actually go about estimating what they are. It's really hard to do this if you don't have a model, right? So going back to the problem of estimating muscle forces, it's very unethical to do this in vivo. Right. First of all, you're not going to have anyone sign up and say, hey, can I surgically implant a bunch of force transducers in your muscles to see what's going on? And so what we end up doing is you do this in animal models, right? So people have done this in rabbits, cats, frogs, stuff like that, while again in cadavers. And we can model the physiological properties of muscles. So things like the force velocity, force length relationships, stuff like that. And we can take that and the mathematical concept and then put that in a computer simulation. And then the other thing that we can do, so from my perspective, we have to take a slight step back and get a little bit into some of the theoretical perspectives on force control. So I took, and a lot of people in the biomechanics space will take an engineering approach where we assume that the nervous system is trying to optimize for a given task. Maybe it's minimizing some type of criteria. Maybe it's maximizing it. However, that's not everyone accepts that. There's a lot of different theoretical perspectives in motor control. That's just a way to go about solving for muscle force. And one of the reasons that we have to do that is there's something called the degrees of freedom problem in motor control. So just, I think a very simple task is think about doing a biceps curl. Think about all the muscles that across the elbow that are involved in elbow flexion. And the question is, okay, which of those muscles are contributing the most to the task? How's the nervous system solving that? We have physiological principles like size principle. There's some evidence on like neuromechanical matching, especially more in like respiratory muscles. So there are certain things that seem to be going on. However, we have this very large degrees of freedom problem, right? And so we have to figure out a way to solve that because we have more unknowns than equations. And so there's a lot of theoretical perspectives. And the one, again, that we took was an optimal control approach. And so basically, in order to solve for those equations, we said that we're going to try to minimize muscle activation. That would make sense. Usually the nervous system's coming up with a fairly efficient solution to the task. And then now we can go about estimating the force that a muscle is producing alongside the physiological properties of muscles that we could calculate from animal models and cadavers to come up with a solution in a computer simulation, right? And so people would go about doing this. This is what I did. And then now, once we have an understanding of muscle forces, we can actually see how does that muscle force contribute to the task. So how does it accelerate limbs in different directions or the center of mass in different directions? I think, why is this important? Going back to some of those more basic biomechanical things that we were talking about, a lot of people will look at just joint moments or look at EMG and try to assess the function of a muscle in a given task. Someone will be doing a certain exercise, they'll slap an EMG electrode on and say, oh, this muscle, the myoelectric activity is greater. But it doesn't necessarily tell you how that muscle is actually contributing to the task. It's really just telling you that the muscle's on, how much it's on, when it's on, stuff like that, right? So you can also use that type of info, like EMG info, to put into a musculoskeletal model to make it a little bit more accurate. But in and of itself, it doesn't tell you everything that everyone wishes it told them.
Uh-huh.
So that's kind of where some of my research came in. And then from there as well, outside, once we figure out a way to calculate the muscle forces as a consequence of that force on accelerating the joints, you can also then estimate how a muscle contributes to a contact force at a given joint as well. So historically, a lot of the biomechanical research also did not include muscle forces in the calculation of joint reaction forces, which would drastically underestimate the true force that a joint experiences. So there's a lot of these simplified, going back to the very beginning, there's a lot of these simplified models. They're easy to model. We didn't have, supercomputers to simulate these things. As technology advanced, and as our understanding of muscle physiology and muscle force production advanced, we were able to create basically in silico, like simulated human beings performing a task using some of these biomechanical measures that we can record in a lab as inputs into our model to help, make it a little bit more valid, and then see what the specific values are in the computer simulation.
Got it. Let's peel back some of the terminology here just for some of the listeners who may not be familiar. You're talking about degrees of freedom and solving and efficiency. Kind of philosophically, what we're talking about here is we can see the output because the models are happening with a person potentially, right? So we know that you moved this way and you moved and produced this much force because we've got a force plate, we've got potentially markers on you. And now maybe we want to try to figure out how you moved that way, right? So we're working back from an output kind of algebraically, and then we're trying to figure out maybe what coordination strategy your body used to produce that squat of X amount of force and these joints moving in that way. Can you talk a little bit more about that?
Yeah. So let me back up on the degrees of freedom problem for a sec. So a lot of us are probably familiar with the degrees of freedom at a joint level, right? Your shoulder can translate and rotate, in three directions of translation, three directions of rotation. So oftentimes you'll see, like, if anyone's taken, some type of certificate, there's usually a biomechanics section, and it'll say like the shoulder has 6 degrees of freedom, right? So they're independent variables that are free to vary. That's at the level of the shoulder. This problem exponentially explodes as we get deeper and deeper. So now let's look at the level of the muscle. That was kind of the bicep example I gave. There's a lot of muscles that can, solve that task. Then you can look at the level of the motor unit. There's even more. Then you could look at the level of like the ion channels and stuff like that. There's even more, right? So you have this explosion of degrees of freedom problem at different levels. And so one of the things that we're trying to guess, this is just a guess for scientists. We don't really know what's going on, is how is that problem being solved? How are all those degrees of freedom being coordinated? There's a lot of different theoretical perspectives in motor control on how we do that I could go into if you feel like that would be helpful. And then again, the approach that we took was, okay, maybe what's going on is there's some type of minimization criteria. Maybe that's what the nervous system's doing. We don't necessarily know, but it seems somewhat physiologically reasonable. And so, other scientists have taken that. There's a lot of debate about even within the optimization criteria, what should we be optimizing for? Should we be optimizing for performance? Should we be minimizing jerk? Which is like, another derivative of acceleration, which, think about like steadiness or shakiness of something. Should we be, minimizing pain? Like, no one really knows. And also, maybe the nervous system isn't minimizing anything. Maybe it's just searching for a good enough solution, right? Something that works. And another thing that is not always considered in these biomechanical models is the role of movement variability. And so this kind of goes back to some of the classic biomechanical things. People usually have this ideal technique in mind of like what a squat should look like. It should look like this. People say, oh, you have like a textbook squat. However, when you look at the variability, even in a very trained person, it varies task to task. And this goes back to the degrees of freedom problem. And it's called repetition without repetition. So you can continue to do the same thing, and sure, from the outside, it looks pretty similar. But if we were to actually measure these things, there are variations in this trajectory of the joints with each task. And there's also, again, stop me if I need to, define anything. I'll just keep going. But a lot of times people also don't consider the variability at the movement level versus the outcome level, because they're not the same. So there's some classic studies. One of the fathers of motor control is Nikolai Bernstein. He's kind of like one of the fathers of the modern dynamical systems point of view of motor control. But he would study these blacksmiths, and what he would see is that the hammer on the anvil would end up in the same place pretty much more or less every single time. There's some variation. However, the trajectory of the shoulder, the elbow, and the wrist varied pretty substantially. And so the variables that give rise to the outcome varied more than the outcome itself. And so when we're talking about movement variability and ideal technique, we also have to consider, is the person satisfying the task criteria? Because if they are, that's great. That's what we want them to do. But the way in which they're doing that is probably going to vary each time. And it's hard to model those things as well. There's some newer techniques in biomechanics people are using to get a better understanding of that.
Wes, that connects pretty well to our understanding of cueing to some degree, where we see that, if our body is kind of below our level of consciousness, figuring out how to accomplish a task, cues that are related to the external task seem to enhance performance. If we're talking in like higher force output, higher velocities, et cetera, more accuracy, when we focus on the external fact, not the internal. And there's some debate around if we're trying to actually just hypertrophy the pec, maybe you would have an internal focus, but having an external focus and cueing like push the floor away, or try to, you're squatting, but I want you to try to imagine you're jumping off the floor or something like that. That wasn't a great example, but external cues being superior to internal cues give some kind of indirect support that this is how things are going on in the body. We're not thinking about, oh, I need to flex my shoulder when I'm climbing this tree. We're trying to reach for a branch and be accurate in that. Do you think those things are connected?
Yeah. So there's one of my buddies who's a professor at Arizona State University does a lot of stuff with like motor control theories, and the theoretical approach that you adopt and the coaching philosophy that you adopt. There's usually some type of relationship between the two. But yeah, for the most part, it seems like when you adopt an internal focus of attention, it worsens performance, at least like you were saying, for most things other than hypertrophy. Some of the hypertrophy stuff is still, in the air, like you were talking about. Seems to improve rep performance, velocity, accuracy, repetitions to failure, all these things. Same thing with constraints. And so even if you don't say something, but you modify the environment to have an individual kind of search a solution space, you see some types of benefits. And so you shift your focus of attention externally or towards the task. Typically helps. Some of the stuff that you see with the internal focus of attention would be higher levels of like co-activation and stuff, right? So like if you're telling someone to squeeze their bicep, you might see their triceps activity be a little bit higher compared to if you tell them to move the dumbbell as fast as you can. You might see that the triceps activity is a little bit less. But yeah, so this kind of bridges the gap between action and perception. And so this is one of the things that is oftentimes not considered in biomechanics as well, is usually when we're making these biomechanical models, even, me during my dissertation, we're really only focusing on the motor side of things. We're not talking about how we perceive the environment or perceive what our bodies are doing, which also plays a role in the motor response. So from a motor control point of view, it's very hard to separate action and perception. And oftentimes biomechanists do. They just kind of ignore it, right? Which is also, it's funny, like if you go to a biomechanics and motor control conference, usually people are really mad that you're not giving, perception its fair shake.
Mm. So what are the kind of dominant theories right now, the closest thing to consensus we have as to what's the way we should be viewing motor control?
Yeah, it's tough. I don't know if consensus always means correct, because the dominant view in motor control and neuroscience from a motor control point of view is the cognitive or information processing perspective. So I could give it just a very brief description.
Yeah, what is that?
Yeah, so essentially you can think about your brain as a computer, right? So it takes in information from the environment. However, from their theoretical perspective, they think that the information in the environment is impoverished. It's meaningless. And they think that the brain has to add meaning to it. So this is usually in the form of something called a representation. Sometimes this is called the homunculus, or like the little man in the machine that will get us to the machine. There's some philosophical issues with that. And then there's usually some type of linear process. It's not always linear, but some type of, program selection, or, there's usually a perceptual stage, like a decision-making stage, and then a programming stage, at which point a stored motor program stored somewhere in your brain. We don't necessarily know where it's stored, or maybe, in connections between neurons, maybe in certain structures in the brain. We're not quite sure. I'm not even sure if motor programs actually exist. But then it's run out. And then your body basically, operates, based on that motor program. There are a few issues with that theoretical perspective. People are, obviously constantly working on these theories, making them better, trying to address some of these limitations. But one of them would be the storage problem. It's like, do you need a motor program for every task? Do I need a motor program for tying my right shoe and tying my left shoe? Do I need a motor program for, writing with this hand when I go across my body and this hand when I go across the other way? Right? It seems to be an issue. There's also something called like the novelty problem. Well, what if we've never done a task before? How do we have a motor program for it? And so one of the, more modern accepted views of this is, well, maybe it's a generalized motor program. So rather than it being just a motor program, maybe there are aspects of the program that can change. So there are invariant and variant structures. So some of the variant structures are obviously things that vary, and the invariant ones would be things that are maintained. So for example, an invariant structure would be, the relative force or relative timing. If you were to write your name with your right hand compared to your left hand, it's going to look a little bit different, but the relative force and the relative size of the letters will probably be the same. Same if you change a different effector and write it, right? And so that's kind of that view. I think in general, it's pretty brain centric. It doesn't really consider the body that much, compared to the brain. And information is impoverished in the environment. And then we have more ecological psychology and dynamical systems points of view, which think that they give less of a role to the brain. It's a part of the process, but it's not like the end all be all. And what they think is it's usually an interaction, like movement emerges as an interaction between the task, the environment, and the organism. There's no stored motor programs. These things emerge. It's like a flock of birds, flying. There's based on local interactions and rules, no programs. Like patterns can emerge without a controller. So they call it being regular without being regulated. And that they're soft assembled. So that means they're like a temporary collective and then they kind of disappear. It's kind of what these patterns are. They're in synergies. And so maybe it's rather than each muscle being controlled independently, they're being controlled in, these collectives to solve a task. And the way that they view the environment is that there's meaningful information. You don't have to add information. You can pick up, rather than being an information processor, you're more of an information detector. So there are key differences in how both theoretical perspectives view perception, key differences on the role of the brain, and there's also key differences on variability. And so from a dynamical systems point of view, usually variability is thought of as like exploration. It's a good thing. Maybe the system's trying to find a better solution. And from the information processing point of view, historically, it was thought of as noise, right? But, some more modern takes, understand that it can be useful. Sometimes adding noise to a signal actually amplifies the signal. This is called stochastic resonance. And so some people think that, okay, maybe there's a functional use for noise. And so this, I think maybe some of the original things in biomechanics and the way we coach biomechanics comes from those roots of the way that we viewed ideal motor programs. So there's this ideal of what it should look like, and noise needing to be eliminated, so reducing variability. Whereas some of the more they're newer, they're still not even that well accepted, to be honest with you. The dynamical systems point of view, there's a growing community of people in that space, but I wouldn't call it the dominant space. They view variability rather than being like white noise, that you listen to. Noise can actually have a structure, can have a fractal structure. So if you think of like a piece of broccoli, that's a geometrical fractal. But you can also have statistical fractals. So something at, 1 second might resemble something at 3 seconds, 30 seconds, 30 minutes, 30 days, stuff like that, right? So there's long-term dependence in the signal, correlations in the signal. And that structure of the noise can change with task constraints. So, if you're doing a very light load when you're squatting, for example, there's probably way more ways to accomplish the task. You'll probably see more variability. But as the task constraints change, let's say you go to like a 1RM, there are probably less ways you could mess up, in order to accomplish that. So you might see that the solution space of all possible solutions constraints to a narrow space. And this is where some of the more, I would say modern theories of, injury come into play with like movement, variability, injury, overuse hypotheses. People think that, okay, well, maybe since some of the biomechanical predictors that we've talked about haven't done a fantastic job of predicting injury, maybe there's something else. Maybe it has to do more with the variability in the movement and the amount of time. And the reason why is they'll study people who, are injured or in pain, or this even goes to people who have like, VTAC or, other issues with their heart. You can look at basically the statistical variability, and you can see that oftentimes people who are in a disease state will either have like fairly regular, like almost too regular, or fairly random variability, whereas people who are somewhat healthy kind of have this middle range, like they call it like complexity. It's not fully regular, it's not fully random, it's kind of like in between the two. And so people think that, okay, well, maybe health is somewhere in between there. That's kind of vague, nebulous. It needs, more, again, prospective studies to look at. But that's where some of these more emerging things are starting to come from, is looking at these more statistical structures of variability.
Well, I think once again, there's some interesting indirect empirical support. If we look at the literature on varied practice versus specific practice, or random or blocked practice. So for those who don't know, there's a fair amount of studies, only a few in lifting, unfortunately, but where they're looking at dart throwing as an example, or other throwing tasks or accuracy tasks, where giving the person the same distance, target, and timing and number of throws, for example, is actually not as good at developing that task as varying the distance, varying the order, and having things actually even interrupting the learning process. So that's, I think really interesting when you see that if we do have, I think that's indirect support for the idea that we don't have specific motor patterns or motor programs, but rather at least we have generalized, if not kind of that emergent motor program, where if the learner is exposed to more variability, like you said, that is not just noise, it's not just a distraction, but it is potentially facilitative as they're able to accomplish the same task in different environments to kind of solidify, quote unquote, that skill, especially for tasks that occur in a more varied environment. Like for a team sport athlete, cutting, it's going to be in response to some type of stimuli. So yeah, I don't know if people are familiar with the term contextual interference, but there's interesting data showing that, I'll give you an example of theoretically what this might look like. You do bench press, and then you read a chapter of Tolkien's Lord of the Rings, and you go back to doing bench press. For a beginner, that's going to be a significant distraction, and they have to relearn and re-memorize how to do that pattern again. And while that interferes with performance in the short term, it extends the arc of learning that skill. In the long term, it seems to better solidify the actual learning of that process. And you can sometimes see this play out in different like coaching strategies that have kind of just emerged. Like, for example, some of the Shiko-based programs where you do like squat, bench, squat. You have to come back to squatting after benching. And I think there might be something to that. Or even potentially daily undulating periodization, where on a day-to-day basis, rep ranges change, loads change, and it gives you more opportunities to practice in different environments versus just doing the same movement at the same load all the time. And it's not to say that that can't work or isn't sometimes the best strategy, but I think it's really interesting where we see some of these approaches potentially have some indirect support. And modifying the environment for those who have ever been exposed to weightlifting. Some of the weightlifting strategies to get people to get better at certain aspects of the lift that they're not as good at, they force the person to solve, much like we do in a biomechanics equation, to get to the task outcome when we modify the constraint. So for example, if you are someone who needs to get better at the third pull or the getting underneath the bar into lockout on a snatch, starting from the top position where the bar is already at your hips, you have to figure out how to drop low while extending quickly. And so you're emphasizing dropping underneath the bar. While you could manipulate things other ways. You could have a block that you pull from, or you could have it already in the back squat position and just drop underneath it, like a snatch balance. And those weightlifting strategies, while not explicitly using the language of biomechanics, coaches have found that, all right, if I have X problem where the person is not getting this part of the movement the way I'm trying to get them, I'm not just going to tell them to do it differently. I'm going to modify the quote unquote environment by giving them a different starting point, load, or constraint to the way they can move so that they can get there. And there's even data on that suggesting, for example, methods of amplifying the error versus just reinforcing the point. There's a really cool study on this where essentially the idea is maybe your radar for a technique error isn't strong enough. So amplifying an error is, okay, I just watched a weightlifter say overpull. I'm going to tell them to overpull even more so they can feel how that's actually an inefficient technique rather than just telling them, hey, don't overpull. And when those are compared head to head, the method of amplification of error actually outperforms just simply correcting them. So the idea here is that maybe they don't notice that they're shifting onto their toes, or they don't notice that they're cutting their pull short. So you have them shift onto their toes even more, or cut their pull short even more. And now that they become aware of it, they can actually go through the process of correcting it. Back in the day, we used to see trainers do this with bands. Like the person doesn't notice their knees are caving in. So you actually put a band around their knees, pulling them in so they can really feel it. And then that cues them to push out. And then you take the band away and see if some of that knee cave is corrected, if that's what you're trying to accomplish. So Wes, I don't know, do you think that's the kind of the way that coaching has shaken out anecdotally, and also some of the research is supportive of a less explicit program-based theory of motor control?
Yeah, definitely. And I think that we can get into some of the philosophy, like kind of support some of this stuff as well, and then kind of tie that back to what you were just saying. So I think first off, one of the things that you see that you're mentioning with error amplification, one, errors are important for learning. You want to make sure that the task is challenging enough to where you're actually making errors. If you're not making errors, usually it's not going to lead to better performance or learning. Two, one of the things that you often see, and as coaches, I think we make this mistake all the time where we have word salad. We always want to try to overcorrect. We want to intervene. And to the point where sometimes the athlete becomes dependent on us. And the goal is to increase autonomy and have them be able to identify their own errors. But one of the things from a dynamical systems point of view of why that could be useful is you're actually destabilizing the movement. And so what do I mean when I say this? So there's a couple of terms we'll have to talk about that you see if you're going to ever like read a paper in dynamical systems as it, applies to coaching, you're going to see terms like attractors. And so I'll just use a very brief example and then, do like a classic demonstration and try to apply it back to coaching. So imagine just a bowl, like a salad bowl, and you have a marble. And let's say that marble is a representation of behavior. I know it's super simple. And you were to drop that marble, it's going to go back and forth in the bowl, and it's eventually going to settle on the bottom. Right? So that's called an attractor. Now, people from a dynamical systems point of view will model brain and behavior using, nonlinear dynamical systems and topology as attractors and repellers. So they're thinking of more of it as this landscape, like a geometrical point of view. Flip that ball upside down, you hit the marble. So now the salad bowl is upside down. It's at the peak. You hit the marble, it's going to roll away, and it's going to roll away forever, right? It's not coming back. So it's been destabilized, right? So there's a classic experiment in dynamical systems called the Hacken-Kelso-Buns model. And they did this finger oscillation like this. And so what they would do is they would have people go either in phase or anti-phase, or this might be easier to see, in phase or anti-phase, like windshield wipers. And what they did was they said, okay, we're going to manipulate the control variable, which, in this situation was finger oscillation. Another easy example to think about is boiling water at home. The control variable would be the temperature. So something that takes a system through all of its states, right? And so what they would see is as we start to speed up and speed up and speed up and speed up, eventually the fingers start to sink. They start going in phase. So basically what that means is at low finger oscillation frequencies, antiphase is a stable behavior. But as we ramp up, antiphase is no longer a stable behavior, but in phase is a stable behavior. And as we ramp back down, we don't see that same shift backwards. This is called hysteresis. So it just stays in that attractor. So you can think about this as like the marble situation again, right? You push a marble into a bowl, and it kind of stays there. Now, if I drew a curve, it would kind of look like at slow finger oscillations, you'd have like these little hump, then like a bigger well, and then like another small well. And then as we move that system through its states, at fast finger oscillations, there's only one attractor. The other two disappear. And they actually get to a point where they turn around and become repellers. Now, if we do the same thing with in-phase behavior, as I speed up, it just stays in phase. It doesn't switch, right? So it's stable at slow and fast velocities. And so we can take this and kind of apply it to stable patterns and why it's so difficult to unlearn, certain movement patterns. and why one of the things that we can do as a coach from this theoretical perspective is we could invite certain movement solutions and destabilize others, right? So like, let's say someone is doing something that you don't want them to do, or it might not be helpful. From this theoretical perspective, it would be appropriate to actually destabilize it, make it very difficult. So let's say someone is, jumping and like their knees are collapsing in or something like that. You can actually change the height of one leg compared to the other. So the caving in of the knees or something like that is no longer a stable solution. So people will do this, and again, some of this is theoretical. They'll hope that it'll transfer over. But this is where I say like some more of the modern dynamical systems, motor control people and biomechanists are heading into this idea of how can we manipulate task constraints to look for more stable attractors, destabilize, unhelpful behaviors. And also, again, from a perception side of things, remember that the dynamical systems and ecological psychologist people, they talk about this concept called affordances. So what does the environment afford you? The way that, from that point of view, the way that we perceive the environment is also body scaled. So there's studies on like people walking through doors or taking stairs, it's usually, their approach they take is actually usually pretty highly related to their body dimensions or their abilities, even like hill perception. Like when people are fatigued, they'll rate the same hill as, more steep, or if they're, wearing a backpack, the same hill will be like more steep. So the way they perceive the environment seems to be body scaled. And so what coaches from this theoretical point of view, they'll try to figure out ways to invite, certain affordances so people can pick up on. A classic example of this would be manipulating the rules of a game. So think of basketball, for example. Let's say everyone is, really good at going right, but they suck at going left. Rather than just telling him, don't go right, you could change the rules of the game. You could say, we're going to have any left-handed layup is going to be worth double the points, right? Mm-hmm. Or you can cut off half the court, or you can make it very difficult, or you can have them put their hand behind their back, rather than specifically telling them. So you can change the strategy. So there's more ways as a coach, rather than just explicitly telling someone, this is what I want you to do with your body. This is how I want you to do it. You just change the criteria. And so that's, again, another thing that you'll see in the dynamical systems coaching perspective. Constraints, changing. And these could be not just game constraints. They could be constraints with implements and tools. So you can see, like, you can change racket size, or bat size, or golf club size, or like a lot of these different things. And oftentimes, not necessarily immediate performance will improve, but again, long-term, learning will improve. So these are just other strategies that you can implement. Going back to like a weightlifting example, there are some studies, obviously the Olympic lifts are, pretty hard to teach. And so rather than just giving so many cues, like so many people do, and especially so many internal cues, I still see people giving so many internal cues. You can, let's say someone is, jumping forward or jumping back, or their bar is swinging way too far out in front of them. Rather than just telling them all these things, you could, draw a box around their feet and be like, don't jump out of the box, or you could put a foam roller in front of them and say, don't hit the foam roller. Right. Mm-hmm. And so there are things that you can do that minimizes just the word salad you give as a coach to help the individual find a solution to the task that works for them. So you see that a lot of times with this theoretical perspective.
Omar, how many times have you seen at a powerlifting meet, some coach is like, they act like they're the puppeteer, for the person, like, all right, hips, squat down, up, racket, wait for the command. And I know it, like, it gives the coach a sense of control and purpose, and it's more for themselves, the self-soothing. But I think at best, the athlete is completely ignoring the coach and just doing what they need to do unless they're a rank novice, or they have like, hey, can you give me this specific cue, like when I've hit depth, because that's one thing I have trouble knowing, which is fair enough. And at worst, if you take a novice, it's actually like messing them up and making them think too much and slow down and end up like doing a pause squat. I don't know how often you still see that.
They have the keys, the coach. You have to listen to every single key that the coach says. And if you only implemented it perfectly, you would have performed the task exactly as you should have. I actually do think it's falling slightly by the wayside. I'm sure, Eric, you could cite maybe some research just about like loud motivational yelling. And that just like when people are competing and they hear that, and when you're competing these days, there's just so many people saying things. I think unless it's inside of a gym, I think Eric, it actually occurs almost more in a gym when someone's trying to hit a PR, like they'll say hips, kind of back in the day from squat suits saying like the hips, and then they'll say drive or something like that, right? Where it's like nonsensical. Whereas I think, I hope I've seen recent like worlds or like nationals or whatever, where it sounds, at least to me, there's less cueing and more like general motivational words. You know what I mean? Like when you see Pana coaching one of his athletes, he's not saying like hips, like knees forward, like 10 years ago.
100%. Yeah, it's an interesting thing. And I think also some of this stuff applies almost more broadly to behavior change. Kind of the idea that your behaviors are a product of a lot of things, including your environment, and just trying to brute force change it and think about it. Like, of course, you do have to actually make a decision or try to put an effort to do something. But like the idea, like a lot of the studies on nutritional habits based upon the environment, like if there is a lot of food just sitting out, you're more likely to eat it than if it's in the cupboard, right? If you have to go walk to do something versus drive, or if it is higher and just out of your eye line, or if there is smaller portion sizes, smaller plates, smaller spoons, like the data is a little bit mixed, but on the whole, it suggests that when you make it less convenient to do something, the behavior changes, and it gives us, it is somewhat more in line with our understanding that we're not the perfect central governor of all of our own behavior, that many times we're reacting to our own decisions that are influenced by the environment. So it's kind of like, well, let me lead myself to different water and then maybe I'll drink that, as a kind of idea. But of course, there is a decision at some point. So I think it's really fascinating that our understanding of motor control is starting to understand, or starting to parallel our understanding of behavior change. And that, of course, should influence what do we do as coaches and what do we do as practitioners. Because one thing that is absolutely true is that unless it is the specific barrier, giving someone knowledge or education doesn't reliably change behavior, right? And I think we can see that even now more so than ever. We have all the information out there. In fact, we have information overload where people don't know the difference between correct and incorrect information. But even people who do have the correct information don't necessarily act on it because there's friction, there's a challenge, their environment isn't conducive to it, or they have an established way of doing things that they don't know how to de-establish, which is, like you were saying for motor control, well, okay, we need to make it harder or not the most obvious thing to do to result in that behavior change to kind of repattern a movement. So anyway, I just find that philosophically fascinating, Wes.
I think another couple of things, piggybacking off what you're talking about with the distinction between performance and learning and autonomy. And so one of the other things that you see that's fascinating is you can yoke two groups together, give them the exact same cues. One group picks when they get the cues, and the other group is just yoked to the same time period that they get the cues. Same information, same coaches, same task. The group that had a choice shows better learning, right? So this also plays back into some of the theories like self-determinations theory and stuff like that, and having some autonomy and control and being a part of the decision-making process. I think that's really important rather than taking this top-down approach as a coach or whatever, role you play in life. If you're in a position of, authority, making sure that the individual is involved in the decision-making process. It's the same thing, with medical doctors in the clinic, athletes, whatever, students, they have to play a part, they have to have enough autonomy. I think with one of the things that Omar was saying at the powerlifting meets, I think something that's really interesting is what happens on meet day is probably going to look different than what happens during training. And so when we're training as a coach, I think it's very important to make sure that we actually start to take a more hands-off role. And so what I mean is there's a lot of studies on the frequency and timing of feedback that we give and like when we're giving it. So are we giving the feedback during the task? Are we waiting till the task is done? Are we giving a feedback of each rep, a summary feedback, whatever? There's a lot of different ways that people can study feedback. And what we see is, not all studies, but a lot of them show that if we're giving too much feedback, we might acutely increase their performance, but it impairs their learning, right? So we can't confuse performance and learning. Classically is, teaching a few classes. I see this all the time where someone crams for a test. They do really well on the test, so their performance is great. But then you come back and do a retention and transfer test and it's terrible, And so performance and learning aren't the same thing. And we have to make sure that we can distinguish between those two things. And a lot of the times we can only directly measure performance and we have to infer learning from it. So that's why we need acquisition, retention, and transfer tests. Needs to be some type of permanence to learning. However, on game day, motivation plays a role in performance. And so just screaming anything, it doesn't even really matter what words you're saying. If it's hips, if it's just random words, that might influence performance. And so as a coach, I'm not worried about what someone's doing on game day. Like if they want to say that, go for it. But if you're doing that in every single practice that you're working with the person, I think that's probably a detriment because you want them to be able to identify their own errors, be motivated and not rely on you all the time for, feedback after every single trial. So what I do and how can this be applicable is I'll usually do some type of banded or faded feedback. And so my bandwidth feedback is I'll have like an arbitrary criteria of what I deem acceptable. If it's in that range, I won't say anything. Sometimes acts of omission are better than acts of commission. But no one ever gets recognized for acts of omission. No one says, thanks for not intervening, right? But a lot of the times that's the best decision you can make. And then I'll also do faded feedback. So maybe when someone's a novice, the amount of feedback that they need might actually be a little bit more. But as they go from a novice to intermediate to advanced, you should be pulling that feedback away. You should be asking, them. They should be able to identify their own errors. And again, like I was talking about, errors are important for learning. And so we can also manipulate task constraints, environmental constraints, whatever, to make sure that there's an appropriate amount of errors, at each phase that the individual is going through in their lifting career.
Wes, this is a wide-ranging conversation, and there are so many potential places we could go to. I do think with the time, though, perhaps it would make sense to talk more specifically about your PhD and about your research.
Yes.
Just to give a listener an understanding, I think it's, like I said, it's been fantastic how we've gone to all these different points, and there's been many things that we could almost dedicate an entire episode towards. But you're a newly minted PhD. Talk to us about that, man. Talk to us about your research. Talk about the squats, the knees, Knee-bola, which we know it's a thing. It's going to happen to everyone no matter what. As soon as it goes, your knees go past your toes, they're just going to explode. And you're here to confirm that.
Yeah. So funny enough, I got into studying the squat like 5 or 6 years ago. And I think at the time there wasn't a whole lot of stuff. I remember looking at the literature and I saw Eric, and was it Glassbrook? Who was the student that you were in Glassbrook? Like
Daniel Glassbrook
or something like that. Yeah. And that's what I had. But at that phase, that's kind of when I was getting into powerlifting. And obviously anyone who's getting into strength training comes across starting strength, right? In the dogmatism of the low bar squat. And so I was really interested in, is there anything to this? And I remember there was a claim made by, it could have been Mark Ripito, it could have been just another starting strength person, about low bar squats outside of being better, for performance, were better for like your knees, right? Because your knees had less forward travel. And so what I did as senior year of undergrad, I had a fairly large data set. So I had a lot of people come in, novices and trained, male and female, and we did high bar versus low bar at different depths with like 75% of 1 RM or something like that, a commonly prescribed load. And I was particularly interested in patellofemoral joint stress because at the time, that's just one of the biomechanical things people look at and then try to associate to knee injury risk, which again is more nuanced than that. And what we found is there was absolutely no difference between the bar types. However, there was a difference in depths, right? However, one of the things that's really interesting when you model patellofemoral joint stress, contact area is very important. So basically stress is force over an area, right? And so a lot of the historical models, like cadaver models, again, that would model contact area of the patella, would stop at like 100 degrees of knee flexion or something like that, right? And then they would kind of just extrapolate the rest of that curve, based on like the direction it was going. However, I found a really old study where the curve makes a dip and then goes back up, right? So we actually saw that as you got deeper, like parallel actually had like slightly higher joint contact stresses than below parallel because the contact area increases again. It kind of offsets the force. And so again, just goes to show you, it's very important. Like our models are highly dependent on the inputs, the data that we're using. And if we extrapolate too far, we can come up with erroneous conclusions. But again, we didn't study injury. We just studied patellofemoral joint stress. And then from there, I wanted to, go into a master's. I was really interested in movement coordination. So I studied something called support moment analysis, which I won't get into here because it's not really the topic of today, and an induced acceleration analysis, which I continued doing into my PhD. And an induced acceleration analysis is really interesting because it allows us to understand, or at least estimate, the consequence of muscle force production on accelerating your limbs in different directions, or your center of mass up or down or front and back and stuff like that. So you get a better idea of how the muscles are actually contributing to the task. A lot of people have done this before me, but it's usually in gait studies, right? So people walking, healthy gait, older adults, falls, cerebral palsy, maybe taking stairs. The closest thing I think I found to the squat was like a sit to stand, stuff like that, right? So no one has really done that in weightlifting. I think some people at Marquette are starting to do that now, so I'm not like the only one. But at the time, I don't think there was anything. And I was really interested in, how are muscles actually contributing to the squat? Because classically, we think, the quads probably doing a lot of heavy lifting, the glutes, adductors, stuff like that. And I wanted to model that to see if that's actually what's going on. And so what we found was that muscle function, classically, for example, think about, if you open an anatomy textbook, it'll tell you that your calves contribute to pointing your foot downward, right? To plantar flexion. And that's kind of where they leave it. But what we found, and what a lot of the other modeling studies found, is that muscle function is actually highly task specific, and it depends on your current body configuration and how you're interacting with the environment. So for example, if your soleus contracts when your foot's off the ground, your toe points downwards. But if your foot is fixed to the ground and you're doing a squat, it can actually contribute to accelerating the knee into extension at near upright stances. But as you squat deeper, it'll spontaneously change its role and contribute to knee flexion acceleration, right? So a muscle can kind of act as like a gas pedal or a brake, depending on where you are in the movement and how you're interacting with the environment. And so what we found with the squat was that obviously, the quads are producing a lot of force. They're contributing to accelerating the bar up. The glutes are, producing a lot of force. They're contributing to accelerating the bar up. But the soleus actually contributed to the most to accelerating the bar up, which you usually don't think the soleus is, super important for squat performance. I know a lot of people with small calves who have pretty good squats. And so the other thing that you see is sometimes there are non-intuitive findings. And so biarticular muscles can actually do the opposite of their like classic textbook anatomical function. So the hamstrings are classically thought of as hip extensors and knee flexors. However, due to the ratio of the moments at the hip and the knee, if the moment, basically the hip is greater, it can contribute to accelerating the knee into extension. So we actually saw the hamstrings can contribute to accelerating the knee into extension. Not a lot, but a little bit. And so one of the things that's important is that we can't get from just EMG stuff alone, or just force plate data alone, is the intricacies of muscle function coordination that's task specific, that changes throughout the task. Now, I think we still have to be somewhat careful. Eric mentioned earlier that whenever you publish in like a strength and conditioning journal, they want a practical application. So in the practical application section, I speculated and I said, well, maybe, strengthening the calves theoretically could improve the squat. The soleus is pretty important. However, when you're dealing with a complex system, just because you tweak one thing doesn't necessarily mean that input equals output. So the calves could get stronger, but it might not actually improve the squat. The calves could get stronger and maybe the coordination strategy just changes. Or maybe the calves aren't the limiting muscle, like in the squat. Maybe there's something else, that is limiting task performance. Or maybe it's just, a bunch of different things going on that's limiting squat performance. We would need, more, obviously studies to see, if calf specific strength training improves squat performance. And we would need more predictive models. So some of the models that I created during my PhD are inverse models. So inverse models take experimental data as input, and you're kind of just like matching, you're just making sure that, the joint angles that you measured in the lab actually match with the joint angles on the model and stuff like that. But in order to have a more predictive model, you would want a forward-driven model where you can, provide, muscle excitations to the model and see what movement emerges. And I haven't done that yet. So there are obviously a few things that need to be done in order to see if, bigger, stronger calves actually improve squat performance. So that's kind of what I did for the past few years. Also, one last thing is muscle function is also somewhat joint level specific. So even though the soleus contributed to accelerating the center of mass up, it actually contributes, at least in our model, to accelerating the hip and knee into flexion as you get deeper into the squat, which is somewhat counterintuitive because you're like, how is it accelerating the center of mass up while simultaneously accelerating the hip and knee into flexion? That one was kind of a brain teaser. It's pretty dramatically accelerating the ankle into plantar flexion this whole time. So it's possible that maybe it's doing so through the ankle, to be determined. We're not exactly sure. However, that's the other thing is what's happening at one level of analysis doesn't always extrapolate to other levels of analysis. I think I see this in popular science communicators all the time, is they figure out what's going on at one level and say, oh, therefore it's happening at this level. It's like, no, it doesn't always happen. So we have to be cautious.
Yeah, one of the things that really helped me when I first got brought on board to the committee for Wes's PhD is I'm not a biomechanist. I'm a strength conditioning, more generalist, if you will. So wrapping my head around this stuff, Omar, was hard. And they had to kind of like get me on board to even understand the concept of an induced acceleration. And one of the useful things that they described was was actually throwing something, right? So if you think of like a sidearm throw, your anterior delt is going to be moving your arm into adduction, right? And if you were to just let your arm go loose and create a significant acceleration of your anterior delt, the first thing that's going to happen if you're starting in a slightly bent elbow position is your elbow will go into extension. And then as it comes forward, it'll move into flexion. So at different phases of the movement, depending upon how much activity there is in my bicep and my tricep, we can see the anterior delt, which doesn't cross my elbow, is creating an acceleration that impacts both elbow flexion and elbow extension. That's a really simplified way of trying to describe how the soleus, which only crosses the ankle, is impacting joints up the stream at different phases and in opposing directions. Because the first thing I hear when you go, so the soleus is, it's extending and flexing the knee and the hip at different phases, and it's making the bar go up, because I'm like, I don't think your model's right. And we did have some reviewers who had that exact same response, but they're forgetting that there's a lowering phase and there's an upward phase. There's eccentric and concentric impacts. And there's also sometimes just an isometric contraction that allows another joint to move faster into the position, and it's stabilizing. So the complexity of this at all these different levels, it's actually quite challenging to hold in your mind all at the same time, which is why these models are powerful and important. But like Wes said, they are all also to some degree limited. They are models. They're our best estimation, and they're based upon our theoretical understanding of trying to do like task optimization, which is probably the way it works, but it's very difficult to empirically validate that. So it was a really fun experience for me to kind of get dumped into this. And I was able to I really had to put on my science communicator hat, because they had to basically walk me through like a PowerPoint when I first got on board so that I could get to the basic fundamental level understanding. And then I went, okay, how do I get other S&C coaches and lifters to understand this? Which is, why it's taken a few rounds of submissions to certain journals where we have not gotten accepted yet for some of the papers that are coming out of Dr. Goodman's PhD.
It's really funny because whenever I go to a biomechanics conference with people who have been modeling for a long time, they're like, oh yeah, okay. Because other studies have shown like the same, like there's a lot of cycling studies that show the same thing, right? Some weird non-intuitive things, right? Because you always question your model. You're like, okay, is there an error in my code somewhere, all this stuff. And then you look through it like 20 times, you send your advisor to look through, you send it to their friends to make sure there's nothing going on. And it's like, no one can find an error. You're like, well, maybe it's just not intuitive. And then you look at other studies that are somewhat similar, like, taking the stairs or walking when you're pregnant, because it changes your center of mass. And you can see like some of how these muscles are changing their contribution. You're like, okay, I buy this. I just, it's still somewhat confusing. But like Eric was saying, I think this is why it's, when you're trying to understand a complex system like the human body, science works pretty well reductionistically. But when we're dealing with complex systems and interactions, sometimes it struggles. And I think that's where the role of like modeling and simulation comes in. However, like Eric was mentioning, all models are wrong, but some are useful. We make a lot of assumptions of simplifications. In physics, there's a joke called the spherical cow. No cows are spherical, but we'll model them as like the center of mass, right? We model plants, center of mass, all these things to make it tractable and easier to deal with, right? And we try to get rid of a lot of the things that we don't think matter that much, but maybe we're getting rid of too much sometimes, or maybe, there's also a trade-off. Modeling is also an art form. These things have to run on a computer and it takes a really long time. And so sometimes you're trying to figure out, what do I need to include and what is worth just, discarding so this thing will actually solve in a reasonable amount of time.
I love it. Wes, maybe we finish up with, where do you see as the future of us having a better understanding biomechanically of the squat? And where do we need to go to take this to the next phase of a more accurate understanding, so we're a little bit less reductionist?
Yeah. I'll tell you where I would go. If I was to stay in academia, what I was interested in. A couple things. I would probably stay in the musculoskeletal modeling space. I would probably, a few things. One, we're modeling these muscles as linear actuators. We're ignoring lateral force transmission, all these things. Also, with the optimization criteria that we specifically used, it considers tendons as rigid, right? So some tendons, maybe that's a good approximation. Sometimes it's not. So you could change different, cost functions, optimization criteria to see if that changes the solution. You could use the EMG to help better inform your models to, again, constrain that solution space. I would run those training studies, with maybe doing two groups, one group, having the same squat protocol, but then you just throw in some like seated calf raises, with another group and see if that actually improves the squat. I might also see if that changes like the sticking point in the squat. I think that'd be kind of interesting. But one of the things that we didn't consider that I had spent a decent amount of time talking about in this podcast is the role of movement variability. I think movement variability is fascinating. I think that there's a decent amount of space to explore in terms of performance and injury risk reduction. So I'd probably do some nonlinear analysis of movement variability. There's a group of people out of Omaha, Nebraska, who have an awesome lab, and they're doing some of that stuff, not in the squat, but in other tasks. So maybe some stuff to do with like the structure of the noise and the signal and how that changes with task constraints, and maybe see how that also relates to people who are currently experiencing an injury, to see, like someone dealing with low back pain or femoral joint stress or something like that, to see how that changes the variability at the task level, but also at like the joint specific level, and how that might change with like light loads to heavy loads. I would love to, obviously run a prospective study where, I don't know if I would love to do this because, you would be trying to figure out who's going to get injured from this study, right? But in order to actually get at some of these classic debate questions on what biomechanical, predictors or variables predict injury, you would have to do something like that. And there's just very little of them. So maybe doing something along those lines.
So like you get a multi-site, maybe a cohort of like hundreds of lifters assess certain biomechanical things over time and then quasi-experimentally group them based into those who got injured, those who didn't, and see if they differed in some of these characteristics. And that's probably the best we can do. Yeah.
Yep.
Awesome. Omar, you got any questions for Dr. Goodman here?
No, I actually think, Wes, you did a fantastic job with so many different points overview. I could tell that you actually, either with the students or whomever, like you have to explain some of these more complex topics by giving like more simple analogies for people to hang on to. I think we should have a follow-up episode, perhaps in the future, something that you alluded to, Eric, at the beginning of our apology tour, where I think there is just in general, Wes, a lot of misunderstanding, both in the evidence-based space, which is kind of the space we're inhabiting, but also like the general space of people. I think in the realm, bros exist in the cracks, as we kind of joked about before. And so there was before like Dr. Gabriel Fendaro talking about like gut health, where there's just not a lot of information out there. And so people presenting certain things, I do think to the general person, there's probably been a misapplication of biomechanics. So maybe going more rudimentary for another episode. But I think all I know is we could go a lot more places. I didn't know, Wes, that we're going to end up on calves. I was following along with you on everything. I was enthusiastic, man. Warhammer 40K. I was excited, dude. And then you're talking about strengthening the soleus. I was like, it has to be anything but this. I guess my final question for you, kind of what Eric joked about. So you're coming up with this modeling. And Eric, when he first reviewed it, he's like, yeah, something has to be wrong here. What were your initial thoughts when you're getting some of this information as it related to the calves and you're just like kind of assessing it, interpreting it? Did you think that there was an error in the system, or had you reviewed so many of these things that you said, like as it relates to cycling or other areas where it could be non-intuitive? Like just out of curiosity, what were some of your initial thoughts when you started interpreting this information?
Yeah, so during my master's, I had ended at the center of mass level where I, estimated that the soleus was contributing to accelerating the center of mass upwards. And then I didn't know what it was doing at the joint level at that time. So you could look up my thesis, and I speculate the entire time that the soleus must be contributing to, basically triple extension, acceleration, the entire time. Like that's how it's doing it. And then when I figured out that I was wrong at 2 joints, I was like, what? How to explain this? And then what I ended up doing is I spent a lot of time looking at similar tasks, right? And honestly, there wasn't a lot of them. Like, again, we're talking, sit to stand. We're talking cycling, walking upstairs, right, with an induced acceleration analysis. And when I saw that the cycling stuff that has somewhat similar, lower extremity joint angles to the squat was showing the same thing with how the soleus can spontaneously change its role, I started thinking maybe I was a little less crazy. Like other people had demonstrated that a handful of times. And then there was a lot of other non-intuitive findings from other modelers, and they had been talking about that. I think one thing too that's really important to know is just because this stuff is getting recognition now, same with like dynamical systems theory, doesn't mean that people haven't been working on it for a long time. There's a lot of studies that are sleeping beauties that aren't appreciated in their day. Like some of my favorite studies on the induced acceleration analysis are from like the 70s, right? Because it's Felix Zajac, who's originally coming out with these, the mathematics behind these things and doing this. And I don't think that, those get the recognition that, people are like, oh, it's crazy that we're just discovering this stuff now. It's like, no, this stuff, same with the dynamical systems stuff. There's a whole group of people working on that a long time ago. And this is where I was saying the consensus statement doesn't necessarily always mean it's the correct statement, because the consensus sometimes in science, even though we want to be evidence-based, there's also a little bit of popularity. There's also a little bit of, a paradigm that's in place that a lot of like the old guard, is keeping. In science is somewhat of a conservative process, like it takes a lot of evidence to change someone's mind. And so things can evolve fairly slowly, but this stuff's been going on for a long time. So some of those original studies and theoretical papers also talked about the non-intuitive findings. And so I think that led to some peace of mind.
Awesome. No, Wes, I really appreciate that. I think we went over motor learning theory. We had a better understanding of how that connects to some things that coaches will actually use, like the number of cues, banded cues, like, hey, don't correct everything, correct the big rocks. And then the amount of corrections should be less from you and more from the athlete as they become more advanced. And that might be why they're becoming more advanced. That you might give specific cues for performance, but you wouldn't necessarily give them for training. And you need different concepts of the environment you're in. Also, the idea that we accomplish tasks rather than moving joints to accomplish a task. So external cues versus internal have a role. And then just the understanding that we are not a cadaver, that we're not a bunch of just isolated muscles that cross specific joints, and that coordinated movement is far more complex than that. That there is a role for modeling despite its limitations, because one thing we probably will never be able to do is actually experimentally induce injury and then see what interventions reduce the likelihood or severity of it. So we're going to be forced to use these acute pieces of data as proxies, then observational work, quasi-experimental work, and modeling to get closer and closer to the truth. And I think it's awesome that you're doing that work, and people should definitely look to follow it as it comes out. So where can people follow you, follow your work, and learn more about this topic, Wes?
That's a great question. I am on Instagram and Facebook, but I am not. I deleted them off my phone so I can spend more time with my family. It's not a great way to run a business. People joke that my gym is kind of like a speakeasy gym. Like,
nice.
If you want to find me, you know how to find me type deal.
Yeah.
So yeah, I am on Instagram. You could follow me there. I'm not very active on it though, to be honest with you. I'll post something like once or twice a year. But I'm on ResearchGate, so any of the research that comes out, follow me there. And yeah, that's basically how you can get in touch with me.
Well, if you know how to find Wes, you'll find him. But next time you're in Bozeman, if you're a serious lifter and you want to go train at a serious place, I'm not going to tell you where to find it. You should know. And absolutely, what I will suggest is be on the lookout. Definitely follow his ResearchGate for Wesley Goodman. Kyle put that in the description. That gets updated automatically, so you don't have to do anything. You can speak and taking care of your new kid. And definitely look for Goodman et al., some publications that have already come out and that are currently being reviewed that are going to be really interesting. I'll, of course, post those on my Instagram once they come out and suggest that everyone consider perhaps maybe doing calf raises if their goal is to improve their squats. But yeah, I think maybe that'll be a good title, Omar. Are calf raises a squat accessory? ?
There's so much that was covered in this episode. I'm positive we could come up with another title. I will say that, Wes, I do genuinely feel that we could do another episode where you're talking about, movement variability, injury risk, but also just some other biomechanical questions. I think, seriously, with the amount that you covered in the time, I think you did a fantastic job overviewing it. So nothing but respect to you. Everything that you've done, the gym that people will have to search to find, but if they find it, there's a safe haven there for lifters, which I really do like that concept. Sometimes the best, like as an example, shout out to other fellow Iron Culture enthusiast, Chip Conrad, with his gym where it's available. Like when he was in Sacramento, he moved. You can look it up, but it's kind of a thing. Like you have to hear about it. And some of the best gyms have some of the poorest marketing. Honestly, just because, to your point, it is truly a passion field project. So nothing but respect to you, man. What you do. I don't think this is the last. The Iron Cult will have heard of you. So even though you're not active on social media, you might be coming back on our podcast. So much respect. Thank you for your time. Thank you to every single person for listening to another episode of Iron Culture. You could go ahead and leave a rating and review. There's no variability here. It's only 5 stars. As far as we can tell, allegedly there are other reviews that are not 5 stars, but we only seem to key in on the 5-star reviews. These days, folks, I'm going to be real with you. 5 stars is not enough to satisfy the host. That's 2023. 2024, it's also the content of what you say. So just be aware you might be, harming one of the hosts if you do something contrary to just leaving a completely glowing review. But we are back every single insert date here from now until the end of time. We'll catch everyone in that next episode. Until next time.